note that if x is a discrete random variable, taking values x1, x2, and so on, then the expected value of x is given as a sigma xi pxi. Pxi means the probability that large x takes value small xi, where I runs all numbers. And if x is a continuous random variable, it is determined by a probability density function. So let fx be PDF of x, then the expected value of x is defined as the integration of small x multiplied by fx in this way. So we will consider some examples. At first, we consider a discrete random variable when we take the outcome when we toss fair dice. So if we toss a dice, then we get an outcome, and we want to the expected value of x. Then this can be easily obtained by making a table, so that x can take values from 1 to 6, and the total probability must be equal to 1. So if you use this formula, then we can easily get you can see that this is equal to half of 7. And now we consider the case that that we have a watch and there is only one leader, like this one, and we want to find the expected value of x. This can be obtained by using this rule. So since P probability density function can be considered as 1 over 12 for x be a number between 0 and 12, and otherwise it is defined to be 0. In this case, by using this rule, you can calculate the expected value for x. So the expected value, which is defined as the integration for x multiplied by fx, is equal to the integration of x. And you can see that this is exactly 6. So you may intuitively understand that 6 should be the expected value, and it coincides with this calculation. Now we consider some new random variable from old one, plus minus. Actually, we can consider multiplication and division, but usually it's very, very complicated if we consider various kinds of new random variables. So actually we just some specific cases, and we will consider how to calculate the expected value of new random variable gx obtained from an old random variable x. So the following theorem can be proved for some specific case, but it is usually very difficult for you to prove the following theorem for the case of a continuous random variable. Anyway, the following theorem says that if x is a random variable and gx is a function of x, for example, gx can be x plus 5 or x squared plus 10 times of x, and so on. And in this case, if x is discrete, and px is a probability mass function, then PMF, then we can show that the expected value of gx is equal to gx px by taking the sum for gx and px. You can get the expected value. In particular, if gx is x, then you can see that it is exactly the expected value of x. And if x is continuous random variable, then E of gx can be obtained by integrating gx multiplied by fx dx. You can prove this just by calculation. It's not so difficult, but if you try to prove this, then it is not so easy, because you should find this part is rather easy, but this part is difficult. Of course, you can consider for some specific case, but usually it's very difficult, because you should find PDF of gx at first, and this process is rather difficult to find. If you replace the gx as y, then usual ey is defined as the integration of y gy, hy dy, where hy is PDF of y. So by definition, if you want to calculate this one, you should calculate this one. But in the process, we need to find the probability density function of gx. If gx is a linear function, it's not so difficult. But if g of x is such a function or more complicated, then you may see that it's very difficult to find the exact probability density function. So it's a little difficult, but if you study real analysis, then you will consider some method theory. If you major in mathematics or statistics in college, then you may see how to prove the equality, but I think it goes beyond this course to prove this one in general case. So we just adopt the theorem without proof. Okay. So I think it is enough for you just to remember these two formula, and you should utilize this formula to solve problems. From this theorem, you can prove the following corollary easily. So let's just take a corollary about related with this theorem. If gx is a linear function like this one, then we can find the expected value easily as following. If A, B are real numbers, then we can show that ax plus b is equal to ax plus b. Okay. To prove this, you should consider the case that x is discrete or continuous. So we only consider the proofs are almost the same, so we only consider continuous random variable x. So I'll assume that fx is the probability density function of x. Then by the previous theorem, we can see that the expected value of ax plus b is equal to, if you consider this as gx in the previous theorem, then you can see that this is obtained by integrating this one. And as a and b are constant, here is x, so here x is the only variable and a and b are constant. Since a and b are considered as a constant, by the property of integration, you can see that this is equal to the integration of this one and sum of b. So we can see that this is equal to aex plus as the total integration of f is equal to 1, we have such a formula. So we can see that the expected value of ax plus b is equal to a multiplied by ex plus b. And let's consider an application of this theorem. For example, if we consider a specific discrete random variable as following, then x is a discrete random variable taking values 0, 1, and 2. Then we want to find the expected value of x squared. If you want to calculate the expected value for this one by using definition, maybe a little bit complicated, so we do not use the definition, but instead we apply this result. If gx is x squared, by using this formula, you can get the solution for this problem. So ex squared can be obtained by this formula, and this is equal to 0 square multiplied by 0.2 plus 1 square, 0.5 plus 2 square multiplied by 0.3. And so you can see that this is equal to 1.7. In this way, you can find the expected value of x squared. And in statistics, it is well known that the expected value of x to the n is very important. And so we define that E of x n is called nth moment. Of course, n is assumed to be some natural number. You may actually prove that the following, and I'm sorry, it's not so easy, but you may later see that a random variable is completely determined by this means, for example, if we know that ex squared and so on, then we can find I'm sorry, if we know these are given and x is a continuous random variable, then a continuous random variable is completely determined by a probability density function, which is the unique CDF. e of xn is equal to the integration of actually I just want to tell you this result, but you don't need to understand what does this mean. It goes beyond our course. Anyway, if you study statistics later, you will see about this. The proof is involved with the Lebesgue integral. You have studied Riemann integral, but there are many other kinds of integration. And actually, in the theory of statistics, the Riemann integral is not so good in calculation. So in statistics, we use Lebesgue integral instead of Riemann integral. You have seen some notations which is not so familiar to you. For example, we have studied this. This notation does not seem to be natural for you, but if you have studied Lebesgue integral, then it is very natural to use this notation. Okay, and then we have introduced this one to introduce variance. So variance in statistics, expected value is the most important one, and to see expected value, we should consider probability, and to see expected value more precisely, we need variance. So we will study what is variance and how to calculate variance and how to apply variance. Okay. We define a variance like this one. If x is a random variable, and we denote the expected value of x by mu usually, and the variance of x is defined as the expected value of x minus mu square. So if x is given, then mu must be a constant, and if you consider the expected value for x minus mu square, if x is already given, then mu is constant, and x minus mu square is a new random variable, and if you calculate this part, then it must be some constant, and it is called a variance. The variance of x. So you may think, why do we need x minus mu square? If notice that expected value of x minus mu is equal to minus mu, and this becomes 0, since e of ax plus b is equal to e of x plus b. From this formula, you can see that this is equal to 0, and so it does not have some information, but usually the variance defined in this way is some positive number, and it measures the variance variance of values, how the value of x are scattered, and if you take square root of variance, then it is called standard deviation. Actually, variance is a big number usually, so in many cases it is better to consider the standard deviation. So actually the information contained in variance is the same with that of standard deviation. Although the variance is defined in this way, it is usually a little bit complicated to calculate the variance just by using this definition. So we study some simpler method to calculate variance. The following theorem gives us a method to calculate variance much easily. So if x is a random variable, then you can calculate the expected value by definition, and you can also find the variance as expected value of x squared minus mu squared. Mu is equal to the expected value of x, so this is equal to this one. And you can also prove that the variance of ax plus b, where a and b are constants, it can be easily proved just by applying the previous theorem and the definition. For example, let's prove the particular top. Consider only the case continuous. In the case x is discrete, it can be similarly proved that fx, a continuous random variable, is determined by a probability density function. So we do not see what the probability density function of x, but we see the existence by definition. So let's assume that f is a probability density function of x, then the variance of x is by definition where mu is the expected value of x. Then by the theorem that E over gx is equal to the integration of gx multiplied by fx. By applying this theorem at here, you can see that this is equal to the integration of x minus mu square multiplied by fx dx, and mu is considered as a constant. This is equal to, here x is the only variable at here, and so you can see that this is equal to x squared fx dx minus twice mu integral x f x dx plus mu square multiplied by the integration of f, like this one. And so by applying this theorem again, we can see that this is ex square, and this part is turned like this one, and minus twice mu. This is equal to mu by the definition of expected value, and as the total integration of f is equal to 1, this is equal to mu square, and so we get the formula like this one again. Now this is equal to mu. Okay, so we have proved the variance of x is equal to the expected value of x square minus the square of expected value. The second one is also proved by using this formula and the definition of variance. It's better for you to replace ax plus b with y, and then you can easily prove it. Okay. Then let's consider how to calculate the variance for discrete random variable as a following. So x is the number that we can get when we roll a pair of dice. Then we want to find the variance of x. So how to calculate the variance of x? We have studied this theorem, so we will apply this result to solve the problem. And so to calculate ex square and ex, we need the definition of ex and theorem to calculate the ex square. So we start with the table of the probability for the random variable x as following. So x can take values from 1 to 6. Ex square is calculated by the previous theorem, xi square pxi, and so this is equal to 1 square multiplied by 1 over 6 and 2 square multiplied by 1 over 6 and so on. 6 square multiplied by 1 over 6, and this becomes 91 over 6. And if we calculate the expected value, which is defined as this one, and this is equal to this is equal to 7 over 2, and so we can see that the variance of x is equal to expected value of x square minus ex square is equal to 91/6 minus the square of 7/2. And so this becomes 35/12. In this way, you can find the variance. And if you take the square root of this value, you can get the standard deviation. We have studied what is a random variable, and a random variable can be classified as a discrete or continuous random variable. And for these two cases, we have studied how to calculate the probability by using probability mass function for the case of a discrete random variable. And for the case of a continuous random variable, we can find the probability by using probability density function. And of course, the CDF, which is a cumulative distribution function, can be used to calculate probability. CDF is usually denoted by large F, which is defined by the rule large F over A is the probability that X is less than or equal to A. And then we have studied what is expected value of a random variable for discrete one and continuous one. And we have studied what is variance and how to calculate the variance. In many cases, it is better for you to calculate the variance by using this theorem. Of course, sometimes it's better to use just the definition of variance, but in most cases, this result is much better to find variance. And in the next class, we also have studied how to calculate the expected value of gx. And in the next class, we will study binomial distribution, normal distribution, and for these two distributions, we will study how to calculate probability, expected value, variance, and their applications. Okay. 오늘 수업은 여기서 마치겠습니다. 수고하셨습니다.